Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module Microbial Fuel Cells for Azodide Treatment under the paper Energy Related Materials. So after completing this module, you should be able to understand the microbial fuel cells for azodide treatment, microbes used in microbial fuel cells, setup and operation of MFCs, their cell performance, effect of concentration of dye on decolorization activity and electricity generation, effect of pH and dye structure on decolorization activity and electricity generation. So microbial fuel cells for azodide treatment, providing adequate sanitation, clean water and energy to the global population is a socio-economic challenge. Renewable and clean forms of energy are one of the society's greatest need with the advent of electronic gadgets, which are becoming part of our life as daily needs. So researchers are working on addressing these human needs. Microbial fuel cells or MFC technologies represent one of the newest approach for generating electricity or known as bioelectricity from biomass using bacteria. While the first observation of electrical current generated by bacteria is generally credited to Potter in 1911, very few practical advances were achieved in this field even 55 years later. Such devices can convert organic matter to electricity using microorganisms as biocatalyst. In this reactor, microbes in the anode compartment oxidize substrates, generating electrons and protons. Electrons are transferred to cathode through an external circuits and protons through the internal membranes. Electrons and protons are consumed in the cathode, reducing oxygen. So, in contrast to conventional fuel cells, MFCs can generate electricity directly from various substrates at mild reaction conditions with environmental beginnancies. However, experiments that were conducted required the use of chemical mediators or electron shuttles which could carry electrons from inside the cell to exogenous electrodes. The breakthrough in MFCs occurs in 1999 when it was recognized that the mediators did not need to be added. The need for the exogenous mediator for electron transfer limits the practical application of MFC due to the intoxicity and the instability of the materials. However, the significant discovery of the ability of a number of electrochemically active bacteria to transfer electrons from inside the cell membrane to the insoluble electrode with a mediator renders the MFC a viable technology for generating sustainable energy. MFCs were also considered for use in treating water waste. Municipal wastewater contains a multitude of organic compounds that can fuel MFCs. The amount of power generated by MFCs in the wastewater treatment process can potentially halve the electricity needed in a conventional treatment process that consumes a lot of electric power orient activated sludges. Additionally, MFCs yield 50 to 90% less solids to be disposed of, and organic molecules such as acetate, propionate, butyrate can be thoroughly broken down to CO2 and H2O. A hybrid incorporating both electrophiles and endophiles are especially suitable for wastewater treatment because more organics can be biodegraded by a variety of organics. MFCs were certain using microbes have a special ability to remove sulfides as required in wastewater management. MFCs can enhance the growth of bioelectrochemically activated microbes during wastewater treatment and thus have good operational stabilities. Continuous flow and single compartment MFCs and membrane-less MFCs are favored for wastewater treatment due to concern in scale-up. Recycle and reuse of textile waste have assumed importance in recent past our countries. With the rise in the living standards, the demands for textiles and clothing is expected to grow. Like any other industry, this industry also generates all categories of industrial waste, namely liquid, solids, and gases. Various useful materials can be recovered from these wastes by utilization of new processes. Waste utilization in the textile industry is gaining vital importance in India, as international legislations are also to come up into force in our country. It is estimated that 10 to 15% of these dyes are lost in effluent during the dyeing process. Currently, the discharge of wastewater containing dyes is an important environmental problem. Unnecessary properties of these dyes is that they must be highly stable in light and during washing. They must also be resistant to microbial degradation. Therefore, they are not readily degradable under natural conditions and are typically not removed from wastewater by conventional wastewater treatment systems. Azo dyes, which are aromatic compounds with one or more N group, are the most commonly used synthetic dyes in commercial applications. Recent studies have shown that azo dyes contribute to mutagenic activity of ground and surface waters polluted by textile effluents. In addition, these discharges into surface water leads to aesthetic problems and obstruct the high penetration and oxygen transfer in waters, hence affecting aquatic life. A range of physiochemical methods exist to remove color from dye containing effluents. They require significant quantities of chemicals and produce notable amounts of sludge, requiring further handling and disposals. Adsorptions and membrane filtration techniques lead to secondary waste streams which need further treatment or disposal. Both advanced oxidation processes and membrane filter methods can be quite effective for color removal but are energy and cost intensive. A few studies have reported electrochemical decoloration of azo dyes at the cathode from wastewater. Biological decolorization via anaerobic reductive processes present a less expensive alternative but usually very slow and require an electron donor to create the necessary reductive conditions. The co-substrate conditions typically far exceeds the stoichiometric requirement, leading to additional cost and unwanted methane production. In these studies, oxygen was produced from H2O at the anode and the azo dye was simultaneously reduced using proton and electron at the cathode. Such a process has potential advantage in terms of versatility, environmental compatibility, and zero chemical usage. However, chemical catalysts were used in both anode and cathodes in these studies, resulting in higher over potentials at both electrodes and accordingly high energy consumption. Difference between chemical fuel cells and MFCs. The main difference between chemical fuel cells such as hydrogen, oxygen, polymer electrolyte fuel cells and MFCs is that the electricity generation in MFCs arises from the metabolic activity of the microbes. For continuous and long-term operation, MFCs must be run under optimal microbial growth conditions, that is, ambient temperature and pressure, electrolytes with a low concentration of ions and near neutral pH. Maximum current densities of MFCs are typically less than 3 mA per centimeter square. They are significantly lower than that of PEFCs, which are of order of greater than 1 ampere per centimeter square, normalized to geometric electrode areas. Microbes used in microbial fuel cells. Microbes in the anode compartment oxidize fuel lattice electron donor generating electrons and protons. Electrons are transferred to cathode compartment through the external circuit and the proton through the membrane. Electrons and protons are consumed in the cathode compartment, reducing oxygen to water. Table on the screen represents a list of different dyes and sources used in microbial fuel cells. Though most of the two identical chamber MFCs are operated with microbial consortium or with an anaerobic sludge from wastewater treatment, an exception was reported with Klebsiella pneumonia strain L17 from substrain forest sediment. In an air cathode, single-chamber MFC anode chamber is inoculated with a mixture of aerobic and anaerobic sludge. The anodic reaction in mediator-less membrane-less MFCs is constructed with Proteus history for simultaneous dye decolorization and bioelectricity generation. Two different enrichment procedures in which glucose and Congo red were added into MFC subsequently or simultaneously were tested by operating parallel MFCs independently for more than 6 months. Geobacter has been frequently reported to be responsible for power generation in MFC as they can transfer electron directly to an electrode. The existence of Geobacter in the MFC can significantly improve power generation. Therefore, the existence of Geobacter in the MFC with EP2 may be the most possible reason for higher power density produced than MFC with EP1. The presence of sulfate-reducing bacteria of the family D-sulfovibrorensis could be responsible for both azodide decolorization as well as electricity generation under the two different enrichment procedures. Setup and operation of MFCs. An appropriate design is an important aspect in MFCs, and researchers have come up with several designs of MFCs over the years. With improved performance for wastewater treatment, the mode of operation and the component of a typical two-chamber and a single-chamber MFC are shown in the figure on the screen. In both single and double chamber MFCs, anode and cathode are separated by proton exchange membrane. In the anode membrane, the microorganisms oxidize organic matter under anaerobic conditions, producing electrons and protons. Electron transfer via external circuit to the cathode chamber where electrons, protons and electron acceptors combine to produce water. The MFC concept is possible due to exocellular electron transfer, where electrons are passed on from the organism via different mechanisms to insoluble extracellular electron acceptors, as shown in the figure. Electron transfer to insoluble oxides in anaerobic environment is especially important for sustaining growth of Fe3 and Mn4 respirizing organisms. Several organic dyes, certain antibiotics, quinones, riboflavin, sulfur compound shuttles, and even humic substances can function as exocellular electron mediator, thus facilitating respiration via exocellular electron transfer. These mediators are either artificial or are produced by the microorganism itself. A mediator-less MFC does not require a mediator but instead uses electrochemically active bacteria to transfer electron to the electrode. Certain microbes seems to also possess another means of transferring electrons directly without the use of mediator, where special conductive pili are utilized called nanowires. In a two-chamber setup, the anode and cathode compartments are separated by an ion selective membrane. allowing proton transfer from anode to cathode and preventing oxygen diffusion to anode chamber. So as shown in the figure, both the anode and cathode chambers can be gas purged. The anode chamber with nitrogen maintains anaerobic condition where the bacteria grow, and the cathode chamber with the air provides oxygen in solution. The cell performance. The ideal performance of an MFC depends on the electrochemical reactions that occur between the organic substrate at lower potential and the final electron acceptor with high potential. Often, the performance of an MFC for decolorization is characterized using electrochemical techniques such as cyclic voltammetry, polarization, open circuit voltage measurements, chronopotentiometry, and electrochemical impedance spectroscopy by measuring the COD removal efficiencies and Coulombic efficiency of the MFC. The bioelectrochemical calculations are done based on the procedures outlined by Logan in 2008. The actual cell potential is always lower than the equilibrium potential because of irreversible losses. The potential or the current of an electrode can be measured in a potentiostat in order to study the electrochemical response of the electrode at that specific condition. In MFC experiments, the potentiostatic mode of this instrument is often used as voltammetric test, in which the potential of the working electrode, that is anode or cathode, is varied at a certain scan rate. A potentiostat can be operated in a two-electrode setup to obtain the polarization curve or to determine the ohmic resistance using the current interrupt technique. Electricity is generated in an MFC only if the overall reaction is thermodynamically favorable. It is more convenient to evaluate the reaction in terms of the overall cell electromotive force, that is EMF, defined as the potential difference between the cathode and electrode, and it is measured in volts. The cell EMF is a thermodynamic value that does not take into account internal losses. Open circuit voltage, or OCV, is the cell voltage that can be measured using the chronopotentiometry after some time in the absence of current. For polarization, current generation was monitored at various external resistances connected for a few minutes, the reading noted after stabilization, and the voltage calculated using the formula V is equals to IR from the current. So power is calculating uses P is equals to I into V, where I is in amperes, V is in voltage in millivolts. So power density milliwatt per meter square and the current density milliampere per meter square are calculated by dividing the obtained power and current with the surface area, that is in meter square, of the anode. So tables given on the screen shows the performance of some MFCs operated using different microbes and fuels. More advanced requirements can be done when the potentiostat is equipped with a frequency response analyzer, that is FRA, allowing electrochemical impedance spectroscopy measurements, that is EIS. In EIS, a sinusoidal signal with small amplitude is superimposed on the applied voltage on the working electrode. By varying the frequency of the sinusoidal signal over a wide range, typically from 104 to 106 Hz, and plotting the measured electrode impedance, detailed information can be obtained about the electrochemical system. Now, the performance of fuel cell is also evaluated by estimating the substrate or COD removal efficiency and Coulombic efficiency during the operation using the below given equations. So COD is equals to CSO minus CS whole divided by CSO into 100, where CSO represents the initial COD concentration in mg per liter in the feed, and CS denotes the COD concentration mg per liter in the reactor outlet. So EC percentage is equals to Cp by Ct into 100%, where Cp is the total Coulombic calculated by integrating the current over time and Ct is the theoretical amount of Coulombic based on COD removal by assuming 4 mole of electrons per mole of COD. Performance of fuel cell is also determined by calculating decolorization activity using the equations given on screen, and the successful degradation of azo dyes was analyzed by using UV visible spectrophotometer. So DE is equals to CIN minus CEF whole divided by CIN into 100%, and dr is equals to CIN minus CEF into QC divided by NCC, where CIN is the influent dye concentration in millimolar, CEF is the effluent concentration again in millimolar, NCC is the net cathodic compartment, and QC is the influent flow rate of the cathode, that is meter cube per decimeter. In characterizing the performance of a MFC for dye decolorization and electricity generation, the relevant variables are dye concentration, dye structure, pH, external resistance, hydraulic retention time, presence and concentration of co-substrates, microbes and electrode materials. Effect of concentration of dye on decolorization activity and electricity generation. The effect of dye concentration on the performance of MFCs. Their study showed that during the closed circuit operation, decolorization efficiency increased from 78.7 plus minus 0.7% to 35.0 plus minus 2.0%, with increase in the influent dye concentration from 0.19 to 0.70 millimolar. During the closed circuit operation, dye decolorization rate was increased from 2.48 plus minus 0.02 to 4.08 plus minus 0.24 moles per meter cube NCC D inverse, with increase in the influent dye concentration from 0.19 to 0.70 millimolar maintained at constant HRT and pH. The power output increases from 0.31 to 0.60 watt meter cube inverse NCC as the influent AO7 concentration increased from 0.19 to 0.70 mm. A higher dye concentration does not exhibit the decolorization up to 1500 mg per liter in a microfiltration membrane air cathode single chamber microbial fuel cells inoculated with aerobic and anaerobic sludge. At low dye concentration of around 300 to 600 mg per liter, the power generated was not significantly affected, but it severely exhibited the power generation at higher concentration of around 900 to 1500 mg per liter. The dyes not affect the current density significantly at lower concentration, but it severely inhibits the current generation at higher concentration. So, the effect of glucose concentration on color removal. So, when glucose concentration increased from 100 to 4000 mg per liter, dye removal in anodic chamber increased from 42.7% to 77%, and the total dye removal increased from 69.3% to 92.7%. Their results also showed the effect of glucose concentration on electricity production. Power density was decreased at higher glucose concentration, and optimal glucose concentration for electricity production was found to be 1000 mg per liter. Now let us see the effect of pH and dye structure on decolorization activity and electricity generation. Power performance is highly sensitive to the pH of the catholyte. The effect of pH on the power density curves obtained by varying the external resistance from 20 to 50,000 ohms for both MO feeding MFC and air feeding MFC. By raising the pH, power density decreases. The maximum power density reaches as 34.77 milliwatt per meter square at pH 3, whereas the maximum power density was only about 1.51 milliwatt per meter square at pH 9. So, power performance of aerated MFCs was obtained as a function of pH in the cathode. In the work of Liu et al. In 2009, the results indicated that the MO feeding MFCs operated under circumneutral and alkali conditions generated slightly lower power than the air feeding MFC. The power output was also highly dependent on the dye selection. The dye with different molecular structures made a difference in power densities when experiments were conducted at varying pH. So students, let us now summarize what we have learned in this module. We have studied about the microbial fuel cell for azo dye treatment, where microbes used in microbial fuel cells. We have seen the setup and operation of MFCs, cell performance, and studied the effect of concentration of dye on decolorization activity and electricity generation, and also studied the effect of pH and dye structure on decolorization activity and electricity generation. Thank you.